And today she's going to talk about the content standardization annotation from different databases that you're doing to enrich the links data. Today I'm going to talk to you about small molecule standardization and annotations that we've been pulling to enrich the links data and support the integration from a variety of the different links data sets, as well as the different platforms that are being used with small molecules. So real quick to kind of preface why small molecule standardization is important is for something like the links data portal. If I wanted to look at all small molecules in the links data portal, you can see right here that there's 41,727 that have been assigned unique links IDs. Now, if I want to look at the overlap between compounds used in broad assays and Harvard Medical School assays, you can see that now there's actually only 302 small molecules. And then if I further wanted to look at only small molecules that were drugs, known drugs, you see that there's only 29. So this is, to be able to build these queries and understand these queries, you need a standardization infrastructure that can facilitate this kind of knowledge integration and can kind of inform the scientific community on the decisions that they want to make. So, kind of taking a step back, what is the difference between a substance and a compound? So substance is something that is often used from a certain center or a certain assay, which is a small molecule, and is, after a standardization procedure, can be classified into a class of compounds. So PubChem has done a really good job kind of starting this initiative and taking data sets from a variety of different centers and papers and institutions and looking at the experimental variables that they performed with the small molecules and standardizing the small molecules into a platform where then other metadata about the small molecule can then be concatenated and put into a repository for the public. So the way that standardization is often done is through validation, checking the input data, a standardization process that often removes salts and other additives, and then doing structure checking to make sure that what was actually used in the experiment is valid and is actually what they thought it was. So the pipeline that we have and that we have put into place, we, along with Ishika, who's done a lot of this work as well, is we take a center or vendor smiles, we do the desalting, and then we do a canonicalization algorithm to basically put the representation of the molecule into a string format. And then we perform PubChem standardization service, which has an API through PubChem, which allows us to standardize the molecule as well as bring in physiochemical properties and link to any relevant PubChem IDs. And then we compare to the previous release, the last data release that's happened. And if we find out that this molecule has not been released before, we assign it a new LSM ID. And then from there, we have another API that kind of comes in and grabs bioactivity information and any other relevant information that we're interested in about the small molecule to then facilitate more knowledge-based analysis. So just an example, we have, this is lapatinib, and so you have lapatinib used in a broad assay, used in an HMS assay. One of them has salt added. So at first it looks like these are two completely different compounds. But after the standardization, you can realize that they're actually the same thing and should be represented in the same way. So this then gets assigned an LSM ID so that both experiments can be linked to the same small molecule. And real quickly, just to walk you through kind of the pipeline that we have in place. So there's these different, these different links 1, links 2 correspond to the different centers. We do the standardization and the registration on the data. This goes into the metadata registry, which Vass kind of talked about. And then we pull in aggregated bioactivity data, as well as other activity data from a variety of different public bioactivity databases, including Kimball, illuminating the druggable genome, drug bank, PubChem, and we're starting to integrate from other sources as well. And then these are being filled in with different bioactivity predictions that we're building and modeling infrastructures that we're kind of building around the pharmacogenomic space as well as the chemical descriptor space. And these annotations are then being fed back into the links data registry for the public. So just to kind of preface, a lot of this is done through DCIC, which is a great chemical repository linking service facilitated by the EBI. And so it kind of does a lot of the work for us in a way, but also facilitates an infrastructure for building APIs and pipelines around a lot of the identifiers that are mapped through UNIFIN. And Kimball itself is a really great, probably one of the best structured chemical repositories in the way that you can build queries and grab information. And BioGPS, which is just another genomic repository. So what do we know about links compounds so far? So we know that out of all the links compounds, 945 are FDA-approved drugs, 164 are chemical probes, and there's 620 that are classified as PDB ligands. So from this, we know that 14,128 have protein target and activity annotations that we've been able to grab from these public bioactivity repositories, and 124,000 approximately unique target bioactivity annotations, which we have kind of a stringent cutoff for what we can actually grab. There's actually more than that, but this is only data that has a confidence, an activity confidence value greater than a certain threshold, and is only IC50 KB KI. And then lastly, we've done a lot of work working with the drug target methodology, which we're also a part of, mapping these targets and looking at the target space of all the bioactivity annotations for these links compounds. So, we have 659 GPCR targets, compounds that hit a GPCR target, 397 kinases, 149 ionic receptors, and 135 nuclear receptors. With that, I'd like to thank you and everyone at the DCIC and a variety of fine group collaborators and people at the Center for Computational Science. I'll take any questions.